Section: Contents. We, in this paper, delve into the realm of large language models, LLMs, based on transformer technology, which are paving the way toward artificial general intelligence, AGI. These models learn a vast amount of world knowledge by predicting the next word in large-scale web texts, and their capabilities have been expanding through increases in model sizes, dataset sizes, and computational power. After their initial training phase, LLMs can be fine-tuned and optimized to cater to specific real-world applications, such as ChatGPT, Claude, Bard, and others, through techniques like supervised fine-tuning and preference optimization, including reinforcement learning from human feedback, RLHF, and direct preference optimization, DPO. Despite the general proficiency of LLMs in various writing tasks, their ability to produce human-like and creative content, especially in the literature domain, has not been fully explored. To address this, we introduce WEAVER, a specialized family of LLMs, trained and aligned specifically for creative writing. The name, WEAVER, reflects the model's ability to intricately combine linguistic elements, similar to a craftsman weaving threads into fabric. Our report aims to answer 4 key questions: why WEAVER is needed, how it is trained, its performance, and the applications built with it. The need for WEAVER arises from the observation that while generalist LLMs like GPTs are capable of general writing tasks, they often fall short in producing human-like texts in specific scenarios such as storytelling, fiction, and social media content. This limitation stems from both the pre-training and alignment stages, where the models are trained on massive but low-quality web texts and aligned using data annotated by non-professional writers, leading to outputs that lack creativity and human-like style. Moreover, popular preference optimization methods do not adequately enhance the creativity of LLMs. Therefore, we argue for the necessity of training domain-specific LLMs like WEAVER for creative writing tasks. To train WEAVER, we employ a suite of strategies for automated data collection, annotation, and filtering, focusing on diverse, human-like, and stylish texts. We introduce an instruction-backed translation framework and a novel constitutional DPO algorithm for preference optimization, aiming to align WEAVER with the preferences of professional writers and content creators. These methods allow WEAVER to not only follow writing instructions but also to evaluate writing outputs, making it a versatile model specialized in creative writing. Evaluating the creative writing capabilities of LLMs is challenging, but we introduce WRITEBENCH, a benchmark for this purpose, and demonstrate that WEAVER outperforms generalist LLMs in creative writing tasks. Our user study further confirms that WEAVER enhances writers' productivity and helps them produce better stories and articles. Finally, to fully leverage WEAVER's potential in AI-assisted writing, we introduce WAWAWRITER, a human-AI collaborative writing platform that offers a chat interface for diverse writing instructions, human-AI co-editing, personalized writing assistance, and integration with personal knowledge bases. This platform aims to provide a next-generation AI-assisted writing experience that is both helpful and enjoyable. In summary, through WEAVER and WAWAWRITER, we aim to advance the state of AI-generated content in creative writing, offering tools that produce human-like and creative texts while enhancing the AI-assisted writing experience. Section Summary. Large language models, LLMs, based on transformers have become a prominent pathway to artificial general intelligence, AGI, by acquiring massive world knowledge through pre-training and alignment. However, generalist LLMs often struggle to produce human-like texts in specific writing scenarios, leading to the development of specialized LLMs like WEAVER, dedicated to creative content creation. WEAVER is trained using automated data collection, annotation, and filtering strategies to pre-train and align on diverse, human-like texts, resulting in superior creative writing capabilities compared to generalist LLMs, as confirmed by evaluation results and user studies. In addition to training specialized LLMs like WEAVER, it is crucial to build a better human-AI interface to fully exploit their potential, leading to the introduction of 50 WEAVER, an innovative human-AI collaborative writing platform. This platform aims to provide a next-generation AI-assisted writing experience by enabling human-AI co-editing, personalized writing assistance, and integration of personal knowledge bases to enhance the writing process. Section: Model Family. We, the creators of the WEAVER models, have developed a series of language models that are enhanced versions of transformer decoders. Inspired by the advancements in Llama, a widely recognized open-source large language model, LLM, we've incorporated several key features. These include a pre-norm structure with an RMS norm function, SWI-glue for the activation function in the feed-forward network, rotary embedding for positional encoding, and grouped query attention, GQA. The WEAVER model family is available in 4 sizes: Mini, Base, Pro, and Ultra, with the number of parameters ranging from 1.8 billion to 34 billion. We designed these models in varying sizes to cater to a wide range of writing tasks, which can differ greatly in complexity across different fields and applications. All WEAVER models start off with the foundation of powerful open-source LLMs, and we've detailed their configurations in a table. Moving on to how we prepared the models, we focused on selecting pre-training data that would not only be comprehensive but also of high quality. Given that our models are based on already powerful LLMs, we didn't need an excessively large amount of new data for continual pre-training. Instead, we aimed to refine the model's capabilities, enhancing their writing and content creation skills while dialing back on others like mathematics and coding. Our pre-training data includes a variety of manually verified sources such as books, fiction, stories, news articles, academic papers, reports, and social media content. We employed both rule-based and machine learning techniques to weed out low-quality texts. We also paid close attention to the balance of data from different domains, mixing fiction and non-fiction in equal parts, and combining Chinese and English content in a 4:1 ratio to ensure the models are proficient in both languages. When it came to training the WEAVER models, we used a standard autoregressive language modeling approach, where the models learn to predict the next word based on the context of the preceding words. We trained the models with a context length of 4096, shuffling and merging documents before truncating them to create training batches. To enhance computational efficiency and reduce memory usage, we incorporated technologies like Megatron, DeepSpeed, and Flash Attention. We chose the Atom W optimizer with specific hyperparameters for beta 1, beta 2, and epsilon, and employed a cosine learning rate schedule, starting with a peak learning rate and gradually reducing it to 10% of that peak. All models were trained using B-Float16 mixed precision to ensure stability. Detailed pre-training configurations for each model size are provided in a table. After pre-training, the WEAVER models possess a vast amount of world knowledge and writing skills, enabling them to generate human-like text based on high-quality context. To leverage these capabilities for practical applications, we curated a high-quality dataset for alignment. The quality and format of this dataset are crucial for determining the range of abilities and the quality of the aligned models. Unlike the common practice in aligning data for generalist LLMs, which often limits their writing capabilities, we adopted a different approach. In the alignment phase, we aimed to unlock specific abilities in the WEAVER models. One key ability is following writing instructions to produce texts that are not only human-like but also stylistically appropriate across various domains and tasks. We focused on several domains during data collection and alignment training. Fiction writing. This includes writing stories and fiction of various lengths and genres, such as sci-fi, romance, fantasy, horror, mystery, and thriller. Creative nonfiction writing. This genre involves creating factually accurate narratives with literary styles and techniques, covering memoirs, biographies, travelogues, journalism, social media posts, blog posts, news articles, and commentary. Marketing writing. This involves creating business plans, advertising copy, promotional materials, and marketing plans. While the style of the generated text is less critical, creativity is essential to attract potential customers. Technical writing. This includes writing academic papers, patents, reports, etc., where accuracy is paramount. Training in writing can help the model produce texts that adhere to the specific style required for these tasks. Section summary. The less than WEAVER model family greater than consists of language models built on transformer decoders, incorporating recent improvements from the design of Llama, and includes models of 4 different sizes ranging from 1.8B to 34B parameters, trained to support different applications with varying complexities of writing tasks. The pre-training data selection strategies focus on including manually verified data sources such as books, fiction, stories, news articles, papers, reports, and social media copies, while carefully controlling the data mixture between different domains. During the alignment stage, the data synthesis framework aims to unlock abilities such as instruction following, covering domains like fiction writing, creative nonfiction writing, marketing writing, and technical writing. Section: Tasks. We're discussing various tasks that our model, which we'll call WEAVER, is designed to handle in the realm of writing and editing. Let's break these tasks down into simpler terms. First up, we have content writing. This is all about asking WEAVER to create different types of written content, like stories or articles, based on specific instructions. These instructions can vary. They might or might not include context from previous texts and can be more or less detailed. For instance, we might ask WEAVER to write a science fiction story about what happens when humans achieve advanced artificial intelligence. Next, we talk about outlining. Before diving into writing a long piece, it's often helpful to sketch out an outline. This is true for both stories and nonfiction works. An outline helps organize thoughts and gives a roadmap for the writing process. An example task could be asking WEAVER to create an outline for an annual work report. Polishing and editing is another important task. Here, WEAVER is asked to refine a piece of writing. This isn't just about fixing grammar mistakes. It's about improving the overall quality of the text to meet certain standards or styles, such as making it suitable for an academic paper. Then, there's style transferring. This task involves changing the style of a text from one form to another, like turning a story into a script or a report into a speech. WEAVER can do this in 2 ways: using a template that outlines the new style or using keywords and descriptions to guide the transformation. Expanding or simplifying text is about adjusting the length and complexity of a piece of writing. This could mean summarizing a long article into a single sentence or expanding a summary into a full article. Brainstorming is where WEAVER helps generate creative ideas. For example, if you're writing a story and need ideas for a villain, you could ask WEAVER for help coming up with character descriptions. Reviewing involves critically analyzing a text and offering suggestions for improvement. If you have an essay, you might ask WEAVER to review it and provide 5 suggestions to make it better. Instruction annotation is a bit more technical. It's about teaching WEAVER to understand a piece of text and then generate an instruction that could lead to that text as a response. This helps WEAVER learn from a wide range of texts and improve its ability to follow instructions. Lastly, we're training WEAVER to act as a literary critic. This means evaluating creative writing and judging the quality of responses to writing instructions. We believe this will help WEAVER produce better texts. To do this, we collect data on which texts people prefer and use this to train WEAVER. In summary, WEAVER is being trained to handle a wide range of writing and editing tasks, from generating content to refining and evaluating texts. This involves understanding and following detailed instructions, transforming styles, and even generating creative ideas, all with the goal of assisting in the writing process and improving the quality of written work. Section summary. The tasks in this section include content writing, outlining, polishing and editing, style transferring, expanding, simplifying, brainstorming, reviewing, and instruction annotation. These tasks require the language model to generate content, create outlines, improve text quality, transform text styles, revise text length, brainstorm creative ideas, critically analyze text, and generate instructions based on given text spans. Additionally, the model is trained to evaluate the quality of responses to writing instructions and perform pairwise comparisons of two responses, aiming to enhance its ability to produce better texts. Section: Retrieval Augmented Generation. We're discussing a technique called Retrieval Augmented Generation, or RAG for short. This method involves generating responses by looking up and referring to external knowledge or sources. It's a crucial strategy that allows large language models, LLMs, to produce more accurate and well-informed responses. This approach is particularly useful for writing tasks, as it's common for human writers to look at other texts for inspiration when crafting their own stories or articles. However, most current LLMs mainly depend on prompt engineering for RAG and don't train specifically for it during their alignment phase. We think this limits their ability to effectively use retrieved information. So, we suggest adding RAG-aware training data during the alignment process to improve the RAG capabilities of a model we're calling WEAVER. We do this by enhancing 10% of the training data with relevant context that's closely related to the desired response. This teaches WEAVER to write by referencing external sources, making it better at RAG compared to many existing LLMs. Next, we talk about the importance of function calling for LLMs, which is crucial for tasks like searching the internet for references or using editor APIs during collaborative writing between humans and AI. To enhance this capability, we've included an open-source dataset for function calling in our training process. We've also created a new method to generate a wider variety of function calling scenarios. This involves using GPT-4 to create diverse settings with various tools and APIs, then selecting one API at a time and imagining how it could be useful, including what arguments might be needed. Based on this, we train WEAVER to select the appropriate API and generate the necessary arguments based on given instructions and context. We also introduce an improved method called instruction-back translation. The goal here is to align WEAVER with high-quality, stylish, and human-written texts. We start by collecting top-notch stories, fiction chapters, and texts from various domains. We then use a specific few-shot prompt template to create instruction response pairs for different writing tasks. This involves selecting a piece of text, identifying or creating the context for it, and then figuring out the instruction needed to achieve the desired output. For example, for a polishing task, we might take a piece of text, make it worse, and then determine the instructions needed to improve it. Using this method, we've created 500,000 high-quality instruction response pairs across various domains and tasks. We then select the best pairs for further training based on their quality, diversity, and relevance. Lastly, we propose a new alignment method called constitutional DPO. This method encourages LLMs to learn from both positive examples and principled, negative examples, which are created based on feedback from AI. It combines the strengths of several approaches, including training models based on principles outlined by human experts and direct preference optimization without the need for training reward models. We start by having experts define principles for different writing tasks and provide examples that either follow or violate these principles. We then use these principles to analyze and create modified versions of responses that violate the principle minimally. This helps us train the model to adhere to these principles by using pairs of original and modified responses. This approach reduces noise in the training data, especially in writing domains, and relies on high-quality data and expert-written principles for generating negative examples, making the training signals clearer and more principled. Section Summary. The section discusses the concept of Retrieval Augmented Generation, RAG, which involves generating responses by referring to external knowledge or references as context. The proposed approach aims to enhance the model's ability to use retrieved contexts by including RAG-aware training data during alignment. Additionally, the paper introduces the concept of function calling, which enables the model to use tools such as searching the internet for references or calling editor APIs during human-AI collaborative writing. The authors also propose a novel alignment method called constitutional DPO, which encourages language models to learn from preference data consisting of samples from the optimal policy and principled, negative examples synthesized with AI feedback. Section: Data. To gather the data we needed for more focused training, we started by collecting high-quality content created by human writers and content creators. We looked at things like their ratings, how many times their work was read, upvotes, and comments. Using a special method for creating data, we were able to make a dataset that includes instructions for over 30 specific areas and more than 10 different tasks. This dataset also has data for evaluating text generation, enhancing text generation with additional information, and data for calling functions. Altogether, we put together about 1 million samples. After filtering through this data, we chose 400,000 pieces to use for more detailed training. For the training part, we adjusted our models that had already been pre-trained for between 3 to 5 cycles. We used a method for gradually adjusting the learning rate, starting with a very small rate and increasing it, with the exact rate depending on the size of the model. Smaller models used a higher starting rate, while larger models started with a lower rate. We also included a warm-up phase that accounted for 5% of the training. All models were trained with a batch size of 256. After this detailed training, we picked the best model based on its performance on a test set for further optimization. For the optimization stage, we chose the top 500 samples from each subdomain based on their ratings during the filtering stage. These were used as positive examples in our optimization process. We also gathered over 200 principles and examples for each. For every positive example, we created a negative one, ending up with 25,000 pairs of data for preference training. We then continued to fine-tune our models using a standard optimization algorithm, training them for an additional 3 to 5 cycles. This time, we used a linear method for adjusting the learning rate, starting very low, with a warm-up phase that again accounted for 5% of the training. The batch sizes were adjusted based on the model, with the largest model using a batch size of 40 and the others using 32. We chose the best model based on its performance on a test set as our final models. To test the writing abilities of our models, we created a new benchmark called WEAVER, which focuses on the ability to produce creative and human-like text. This benchmark covers multiple domains and tasks, similar to how we collected our training data. To make sure the comparison was fair, an independent team handled the collection and selection of instructions for this benchmark. WEAVER includes over 1,000 test instructions across 4 domains: fiction, creative nonfiction, technical writing, and marketing writing. Initially, this benchmark is in Chinese to test the model's ability to write in Chinese. We compared our models with other leading Chinese language models, including both open source and proprietary ones of various sizes. We used the same instructions from WEAVER for all models and collected their responses. In our evaluation, we first did a broad comparison using GPT-4 to score how well each model followed instructions and their creativity and style. Our largest model outperformed all other proprietary models, including some very strong competitors, in terms of writing style and creativity. However, GPT-4 and another model were better at following instructions, likely because they are much larger. Our other models, even though they were smaller, still performed comparably or better than both open-source models and most proprietary models of much larger sizes. This shows that our method for creating and training data is effective for developing models specialized in creative writing. Section Summary. The dataset for supervised fine-tuning was collected by gathering high-quality content based on metadata such as ratings, reads, upvotes, and comments, resulting in around 1 million samples, which were then filtered down to 400,000 data points. The models were fine-tuned using a cosine learning rate scheduler and a global batch size of 256, and the best-performing checkpoint was selected for preference optimization. Additionally, a new benchmark called 30 WRITEBENCH was constructed to assess the writing capabilities of LLMs, and the results showed that 30 WEAVER Ultra outperformed other models in terms of writing style and creativity, while smaller versions of 30 WEAVER were comparable to larger generalist LLMs. Section: Human Evaluation. We conducted a human evaluation to see how our AI writing tool, WEAVER, stacks up against other leading language models like GPT-4, GLM-4, ERNIE Bot 4.0, and Gemini Pro. We asked 44 professional Chinese writers and editors to help us with this. They compared the outputs of these models based on creativity, style, relevance, and fluency, just like in the chatbot arena benchmark. After gathering 3,540 comparisons, we calculated the ELO ratings for each model. The results showed that these professionals rated WEAVER Ultra much higher than the others in all categories. Interestingly, GPT-4 and Gemini Pro were seen as more creative and human-like than GLM-4 and ERNIE-Bot, possibly because the latter two models were trained using data from GPT, which might have affected their originality. In another study, we wanted to see how helpful WEAVER really is for real-world writing tasks. We had 5 professional writers use WEAVER Ultra and GPT-4 to write short stories on the same topics, and we noted how long it took them. The stories written with WEAVER were completed 3 times faster on average, and a professional editor preferred the WEAVER stories 4 out of 5 times. The writers felt that WEAVER was faster and produced more natural texts, which saved editing time. Next, we introduced WAVER, our new platform for AI-assisted writing that takes advantage of WEAVER's capabilities. WAVER combines the best features of current writing aids, like AI-generated text, polishing, and summarizing, and adds some new innovations for a next-level writing experience. One major innovation is a new interface for writing collaboratively with AI, which acts more like a human co-author than traditional tools. This AI can understand the document's goal, take actions based on the content and user interactions, and even use external APIs for complex tasks. It allows for a more interactive writing process where users can chat with the AI to guide it. WAVER also lets users create personal knowledge bases by uploading documents or saving web pages, which the AI then organizes and uses as references. It can even handle images in documents by captioning them for easier reference. This feature, along with the ability for the AI to access these knowledge bases, makes writing with WAVER a more informed and efficient process. Section Summary. The section discusses the human evaluation of the WEAVER Ultra model compared to other language models, showing that professional writers and editors rated WEAVER Ultra significantly better across all metrics. Additionally, a user study revealed that WEAVER Ultra improved the efficiency of writers by around 3 times compared to GPT-4, generating more human-like texts that required less post-editing. Furthermore, the section introduces WAVER, a next-generation AI-assisted writing platform that integrates key features of recent platforms and implements new innovations, such as a new interface for human-AI collaborative writing and the integration of external knowledge and tools to enhance the writing experience. Section: Personalized Writing Assistants. We've developed a unique writing assistant called WAVER that stands out from other AI writing tools by offering personalized help. Unlike the usual one-size-fits-all approach, WAVER tailors its assistance to match each user's individual writing style and preferences. How do we do this? By keeping a text-based profile for every user that captures their writing habits and preferences, like their choice of words, punctuation, and how long they prefer their sentences to be. This profile isn't static. It gets updated regularly based on the user's recent writings, thanks to a large language model, LLM, and a well-thought-out prompt. When it's time to write, this profile is used to guide WAVER in offering suggestions that feel personal and relevant. Moreover, WEAVER can generate text that goes on and on without losing coherence or creativity, thanks to a technique called recurrent prompting, which is a feature of another tool we've developed named WEAVER. This process involves creating an outline for the text based on the current context and then fleshing out that outline into full text. Users can guide this process by choosing the next outline themselves or letting an LLM do it automatically. This approach is particularly beneficial for writing stories or fiction, as it ensures the text remains creative, consistent, and relevant. In our technical report, we introduce WEAVER, a set of LLMs designed specifically for writing tasks. WEAVER is trained on datasets that have been carefully selected and then fine-tuned to align with the needs of professional writers and editors through a new method of data synthesis. We've also created WRITEBENCH, the first benchmark for evaluating how well LLMs can handle different writing tasks. WRITEBENCH covers a wide range of writing domains and tasks. When we compared WEAVER with over 10 popular general-purpose LLMs, WEAVER Ultra came out on top, proving it's the best option available right now. Our user studies further confirm WEAVER's effectiveness in real-world writing scenarios, showcasing the success of our approach to training domain-specific LLMs.